really weird, but it's kind of cool. All right, so I'm going to move on to the next problem. All right, so this is 2018. So we have a triangle ABC, and then D and E are any 2 points on AB and AC, so that DE is parallel to BC. All right, I might erase this later, but I'm going to keep it for now. So okay, so we draw the circumcircles of ABE and ACB. Okay. So let's see. So oops. O1 is the center of C, and O2 is the center of D. Or is O1, O2 parallel to BC, or is that a coincidence? I think it probably has to be true somehow. I feel like this, oh, not necessarily, just looks true. Okay, so let's draw a diagram where it doesn't look like they're parallel. Maybe if I draw like a tall triangle, yeah, there we go, that looks better. Okay. Line O1, O2 meets AC at P. All right, so let's make this look nice. It meets AC at P and AB at Q. Let O be the circumcenter of APQ. A lot of circumcenters here. And M be the midpoint of the intersection of AO with BC. I wonder if M is also the midpoint of BC. That would be a big coincidence. But let's just check it. It looks like M is the midpoint of BC. Oh, prove that M is the midpoint of BC. That is the problem. All right. So I figured out the problem before even reading it. Sounds good. So yeah, maybe we might want to let M actually be the midpoint and show AO and M, and that AO and M are collinear. That's one way to do it. So yeah, I could let M prime actually be the midpoint. Either way, I guess. Yeah, this is just so weird. Like O1, O2 intersects AB and AC. It is equivalent to showing that the AC median is perpendicular to O1, O2. Really? So does that mean O1, O2 is always parallel to the same thing? Yeah, O1, O2. Okay. So let me think through why that is what you just said. Could you explain why it's equivalent? AO and the perpendicular from A to O1, O2 are isogonal. Is that just an angle chase? Is that so the perpendicular from A to O1, O2 is basically this AF, right? Circumcenter and orthocenter. That I know that. Oh, because okay, so those two are isogonal. So AO and AF are isogonal rays. I agree with that. So, okay, so since AF is perpendicular to O102, it's the same as saying that AO, the AC median is perpendicular to O102. Okay. So we want to show that AF is a symmedian. So that's, I guess if we let this be M prime. Yeah, I like stating it this way better. So let M prime be the midpoint and then show that M prime equals M. So okay. So angle BAF, we want to show it's CAM prime. So BAF is DAF, which DCF, which is DCB plus BCF, which is CBE. BCF and BEF are similar. Is that that's just spiral similarity, right? Yeah. Yeah, so those are similar. So then, so BF over FE is BD over EC, which would be AB over AC. So can we show it's like a harmonic quadrilateral? Yeah. So I wonder, so we have FB over AB is FE over AC. So FB over FE is interesting. But they are similar. Yeah, we don't want to show AFBE as harmonic, but I mean, I guess we want to show that this is harmonic, right? So you know what? AF meets this at its midpoint. I feel like we've done a lot of problems like this before. So this intersection point right here is the midpoint of AF, right? So
actually, we know that the altitude from F to AB and altitude from F to AC, their ratios are equal to ratio AB over AC, and it is well-known property of median.
Okay, so if we drop altitudes from F to both A, B, and AC,
The ratios of distances equals to ratios of tides, and it is well-known property of a point on the C-median.
yeah, okay, so I'm just trying to think how you would prove that. So I know that well-known property. So if you drop the
From
altitude,
similarity, we can prove that ratios are equal from similarity.
okay, so because FBD is similar to FEC. Oh, okay. So if those are similar, then then their heights have to be similar. Yeah. So it's okay. So all right. So that sounds good. So I will write that up. Hold on just a second. Okay. Yeah, I feel like we proved this another way too earlier. So let's see, what points did I add? So I let those two circles meet at point F. And I think that's really all that I added. I don't think I needed this point G for the proof. Let meet at point F. And then we have, oops, angle FBD equals angle FBA equal to angle FEC and angle FCE equals angle FCA B. We gotta add another $sign. All right. And then the altitudes of those triangles are in the same ratio. Oh. Okay, so okay, so I'm just gonna write that statement out. There we go. So that means that all right, like this, the distance from F to AB over the distance from F to AC is equal to BD over AC, which is equal to AB over AC. Where E of P comma L is the distance from P to the line L. And so this means that F has to lie on the submedian. I'll let the viewer prove that if they haven't seen it, but And once we know that, so if we let M prime be the midpoint of BC, okay, so AF is perpendicular to O1, O2. And angle BAF is equal to, so I'll just write up here, let M prime be the midpoint of BC. And so, actually, even before this, so that means angle BAF is equal to angle CAM prime. And so since AF is perpendicular to O1, O2, then basically that means AO. So we know AF and AM prime are isogonal, and also the orthocenter and the altitude are isogonal. So that pretty much proves that AO and M prime are collinear. So I'll just write it like this. So this means that AF and AO are isogonal. And that means that AO and M prime are collinear. As M prime is equal to M. M is the midpoint of BC. All right, so now we'll move on to the next problem. This is a cool one. Let's see. BAF is equal to CAO. Yeah. All right. All right. There we go. And now we are ready to move on to the next problem. So yeah, we use this key property here of symmedians, which I've used maybe like 3 times before. But yeah, it came in handy this time. All right, thanks for the help with that. So here is a problem from 2017. A cyclic quad problem. A, B, C, D. Like China loves cyclic quad problems. A, C, and B, D intersect at E. And A, D, and B, C intersect at F. So let me draw the diagram something like this. So this is not quite a Bricard configuration because it doesn't have the other intersection, but maybe it might be worth drawing it in later. So this is E and this is F. They made the names of the points easy for me, so I didn't have to rename anything, but I definitely will later. Another circle is tangent to EB and EC at M and N. Oh, this is tricky. This is going to be tricky. But I will draw it. So the center of the circle is going to be somewhere on this angle bisector. And okay, so we have another circle. Let me hide some excess stuff. So we know EG is like an angle bisector, right? And it intersects So it's tangent at M and N. And it intersects the circle at Q and R. Whoops. So Q and R. And then lines BC and AD intersect MN at S and T. Oh wow, this is a tricky one. S and T, all right. So it intersects BC at S and AD at T. We want to show QRST is cyclic. Interesting. Hide. Let me make the diagram maybe a little nicer. So see if I can fix this up. It might be as good as it gets. All right, that doesn't look so bad. Power ratio lemma. I think there's possibility that could be used. So we want to show S and T have the same ratio of powers with respect to those two circles. So S and T both lie on the polar of E. I don't know if that does anything. So that means that E lies on the polar of both S and T. Sn times Sm. Yeah, so that would be applying the power ratio lemma. Yes, that's correct. So yeah, that might be a good strategy. Let's see if there's a way we can show that. Maybe. Yeah, the power ratio lemma seems maybe the most natural way, just because, yeah, it's a fairly complex configuration. If we didn't use it, yeah, I'm not sure how else we would do it. So we could also maybe try using the I was going to say like SG squared minus the radius squared, although I don't know if that really helps. Let me let O be the center of the original circle. So yeah, maybe, so yeah, I'm trying to see if we could do similar triangles. ANT is similar to SMB. Really? SM? Ah, interesting. So I can see why one angle is equal. Yeah, ANT is similar to SMB. So that gives a lot of the information in the power ratio lemma, right? Because it means that SB over AT is SM over TM. I wonder if that's like, so yeah, SM over TN is equal to BM. I wouldn't use BM and AN. I would use SB and AT since they're both in the power ratio formula. Yeah, exactly. So yeah, that looks very similar to the power ratio formula. So then we would need to show that one other, because those ratios, like if we rearrange the power ratio, yeah. So it would simplify. So we want to show, I guess I'll write it down in the chat. So once we know that, we want to show that SM over, want to show SM over SC is equal to
The similarities DDM and SCN. Then we are done.
What's the other pair of similar triangles?
DDM and SCN.
DDM and something CN. DDM, or I'm sorry, say it one more time.
DDM
Okay.
and SCN.
Okay. And those are odd. Okay, so yeah. Wow. We crushed this one. Yay for the power ratio lemma. It was a great idea. Move this up a little bit. All right. That was pretty fun. So, first of all, we have angle DMT. Let me think about this for just a second. Angle BMS is equal to angle ANT. So yeah, so we have angle BMS is 180 minus angle TMT or EMN. ENM. And that's equal to angle ANT. All right. And also angle MBS is equal to angle DMC is equal to angle DAC is equal to angle NAT. And so that means BMS and ANT are similar. And so that means that BS over AT is equal to MS over TN. Make sure I did that right. So yeah, BS over AT is MS over NT should be. And then similarly, we have triangle NCS is similar to BMS. I think that's right. Sorry, I know you, let me look at the chat. So TDM and SCM. TDM and SCM, yeah. Triangle SCN. And that means that TM over SN that means that TM over SN is equal to TD over SC. And then combining the two, we get what's in the power ratio formula. So I'm just going to literally copy what Hakan put in the chat for that. I don't know why it's not coming up. Sorry. Trying to get, there we go. Copying it from the chat. Put it in serif. So by the power ratio lemma, STQR is cyclic. Maybe I'll just, for the viewers, write it out a little. So we have the power of S with respect to, what do they call it? Omega 2. So, whoops, sorry about that. So the power of S with respect to omega 2 over the power of S with respect to omega 1 is equal to the same thing but with T. And that implies QRST is cyclic by the power ratio lemma. That is a very, very cool application of it. And that's awesome how quick you guys saw that. All right. So I will move on to the next one. Right. Let me just make sure that when you combine these two, you do get it. Yes. SC TD. Yes. All right. Wow, this is our last problem, but then we could go back to the one that we didn't solve. So we have two non-overlapping circles, gamma 1 and gamma 2. Doesn't even say what their centers are. A and C are on one of them, and B and D are on the other. So I'm going to have to do a little renaming here. So this will be D. Maybe it'll be better. I'll just rename everything. So A. I just want the first circle to be on the left and the second one to be on the right. AC. Oh, I already have D. That's kind of nice. And then point B. All right. Let me call the centers O1 and O2. All right. Oh, they're external tangents. I shouldn't have drawn those points. Oh well. All right. I thought they were arbitrary at first. So yeah, it draws all the tangents, internal and external. So so we have it. Oh man, I gotta rename everything now. Oh well. So this is A, B.
CD is internal.
Ah, CD is internal, you're right. My bad. So I will delete this. What? I have to hide it. It's weird. You can't delete. I have to do it like that. Okay. So CD is internal. I guess it doesn't say what point is C and what point. Oh, this is C because A and C. Okay. All right. Let me hide the excess. Okay. A, C, and BD meet at E. I'll probably have to, oh, that was nice. I didn't have to rename it. F is on the first circle. I guess F is any point. And the tangent line to the circle at F meets the perpendicular bisector of EF at M. That's kind of random. So it's the tangent line. And then if I draw the perpendicular bisector, it almost looks like EF is parallel to AB. I don't want it to look like that. So M, okay. So maybe I'll move, let's see what I want to move around. It's not so bad, okay. So this is point M. And MG is tangent to gamma 2. Okay, so we want to show MF is the length of the tangent from M to the other circle. Which obviously there's two of them. That's the same as saying M lies on the radical axis. I mean, it's the same as saying, yeah, M lies on the radical axis, right? Yeah, I don't know if there's really a point in it's interesting though. So yeah, it's saying that M lies on their radical center. So obviously MF equals ME. I don't even know if it's worth drawing in MI and MJ. We could just call one of them G for the heck of it, because the problem does it. Let me see what you guys send in the chat. I'll draw an MI and MJ and MG, why not? Okay, in the chat, yeah, M lies on the radical axis. So wherever F is, saying that M it has the same power. And E, yeah, it's interesting. Are O1E and O2 collinear? Let's see, maybe they are. It looks like it. Wait, what is G? Oh, yeah, this really should be point G. Oops. But I believe that's true. I'm not sure why yet.
Can you move O1 or O2, I think? Check
Okay.
it.
So, yeah, E still lies on O1, O2. So, yeah, I think it's true. I think this, what is this G2? I think I could just delete it. Yeah. All right. So that's interesting that E lies on O1, O2. Doesn't seem that obvious to me, but okay. So let's make use of the fact that these are tangents.
AC is perpendicular to BD, I think.
AC is perpendicular to BD.
Angle chasing.
Okay. Yeah, it's just yeah, it's just an angle chase. If you want to show that this plus this is 90, and yeah, you can calculate this. So this O1 AC is similar to O2 BD. I don't think that's true because one's acute and one's obtuse. But maybe their angles have some kind of relationship. Yeah. Okay. I wonder what the locus of M is. So you can actually show the trace. So as we move F around, M is like a vertical line. It's interesting. And that vertical line must be the radical axis. So yeah, is it obvious that E lies on O1, O2? surprised I haven't seen that theorem before. That seems like it would be very well known. So yeah, maybe we could try to show AC cuts O1, O2 in the same ratio that BB cuts it. I don't know if, let me check something. Yeah. But yeah, it doesn't, I don't see right away why E lies on O1, O2. You think the whole problem is an angle chase, or just the fact that E lies on O1, O2? Ah, okay. It still says show trace. So yeah, let me get rid of the trace. AB and O1, O2, yes. So that's the X simillicenter, external center of similitude. Let's see. So let's see. How should I do this? That looks. Move this over a little bit. That looks all right. So I is the X simillicenter, or whatever you call it. Homosity center. And so AEI is 90 minus BeO2. Yeah, so then AEB would be 90, like Hakan, or you are Hakan. It would be I think Serdar might have said that they're perpendicular, but yeah. Okay. So once we know they're perpendicular, so yeah, then we'd have like ME is equal to MF is equal. So yeah, if we like drew the circle with center M, it would like pass through all those points. So it's kind of like showing that FJEG is cyclic. I think it might be just the same as showing FJEG is cyclic. Not 100% sure. Oh, we know they're perpendicular, and then that shows that E lies on O1, O2. Okay. Yeah. Oh, yeah. We can't really construct. So yeah, maybe we let the. I'm trying to think. So we draw a circle through E and F. How would we do this? Yeah, we just have to figure out what the other point is. Maybe we could let. I'm trying to think of I feel like this condition is equivalent to something. So basically, we pick a circle through E, and we let it intersect how would this work? Yeah, maybe it's a little trickier. I guess we could like draw the radical axis of these two circles. Yeah, it's tricky. We want to show that for every point on the radical axis. Because yeah, E, and when we move F around, E stays the same. So we want to show that for each point on the radical axis, the distance to E is the same as the tangents to the two circles. It's one way to think about it, I guess. And maybe there's a way to show that ME squared is the power of M with respect to this circle. I guess, yeah, we want to show ME squared as the power of M with respect to this circle. For every point on the radical axis, E lies on the polar of that point. Is that true? Because E doesn't lie on the polar of M with respect to this circle. Oh, that's right. So yeah, these circles would be orthogonal. If we draw this circle, it would be orthogonal. I don't know if there's some theorem about orthogonal circles that might be helpful. So O and F is tangent, and O to yeah. What if I draw the radical axis? So I'm gonna draw it. just sort of forcibly. I don't know if there's a better way to draw it, but yeah, what's the fastest way to draw a radical axis? Like we could get 1 point on it just by drawing a random circle. We could get another point on it the same way. Well, we could get 1 point and then, yeah, draw the perpendicular to 01, 02. So I think that's like the fastest way. Okay, so let me draw the radical axis. And then drop a perpendicular. There we go. That's my radical axis right there. So we want to show for every point on it, if we pick a point on it, then the distance to E is the same as the tangents to the two circles. So maybe I should just hide M for now. I want to make it more dynamic. Yeah, let me hide point M and all these other things. Okay, so we have a point on the radical axis. Yeah, it's the midpoints of A, B, and C, D. So those are both midpoints. Then, basically, if I draw this segment RE, it's saying that this circle is orthogonal to those other two circles. So wherever I move this, it's saying it's orthogonal. It's interesting. So it's saying angle RUO is always 90. Okay, so I draw a circle with center R and radius RE, and then I want to show RUO is 90 degrees. Actually, that would solve the problem, because then it would mean it's also true for the other circle. S lies on the radical axis of O1 and the point circle E. Do you mean the point circle D? Oh, T lies on D and S lies on, I think, B, you mean. Or, well, SA squared equals SE squared. Ah, that's a good point. So yeah, RS and T, or S and T, yeah, lies on the radical axis of those two. We kind of like that idea. So S is the radical center of those three. and T. So yeah, we know ST is the radical axis. Is okay. Okay, I agree with that. So they're all coaxial. Oh, and that solves it. Yeah. No, that does it. Very nice. All right. So I like the use of point circles there. That's a really nice solution. All right. So yeah, that's really nice and really short, actually. Yeah. Some of these problems look intimidating, but yeah, if you find the right idea, it is not so bad. Okay, so I'm going to delete some stuff. Point P, I don't even know what I did with it. Oh, whoops, don't want to do that. What is point P? Oh, that's just how I created the circle, I think. Okay, yeah, we don't need point I either. We don't need a lot of stuff. We don't need point U. Okay, so let S be the midpoint of AB. That means that SA squared equals SB squared. And that means S lies on the radical axis of those two circles. And then similarly, T is on the radical axis of both. And that means that ST is the radical axis of both. And then, but S, I could say SA squared equals SB squared. Yeah, okay, we did have to do the point where E lies on. I think I do need point I, actually. Maybe I already deleted it. Yeah, oh well. I'll have to add it back in. Okay, so first let me show that E lies on O102. So we can use an angle chase to show that AC is perpendicular to BE. So I'm just trying to think how we would do that. So we could show that angle CAB plus angle EBA is 90. So we could first show that. All right. Okay. Whoops. So angle CAB is 90 minus CAO1, and angle ABE is 90 minus angle O2BE. And those angles, that's the same as O1CA, which is do you guys remember how to prove that E lies on O1, O2? And that, yeah, do you guys remember how to prove that? I think it's just an angle chase, but I'm trying to write it out. So show that AE is perpendicular to BB. Okay, so AE, it's perpendicular to the segment from O1 to the midpoint of AC. And BE, yeah, I'm just trying to think how to do it. That trying to remember how to do this. So angle ABD, that's half of angle BO2D. Okay, so let me write this out. So we have angle ABD is half of angle BO2D, and angle BAC is half of angle AO1C. So this, let me check the chat. If you extend DC to meet AB, okay. So then it should be easy. Okay. So then UAC is UCA is DCE. Okay, I'm just gonna copy this in. Whoops, my bad. Don't know why that didn't work. How do I get the chat back? All right. Okay, so we have angle CDE 90 minus DUB over 2. Because, yes, which is 90 minus twice angle ACU over 2, which is 90 minus angle ACU. Okay, so that means that AC is perpendicular to BD. And then from there, yeah, so yeah, because UD is equal to UD. Yeah. We don't need a Schroeder collinear. We just need the perpendicularity. Interesting. Okay. So then I'm going to delete that step. We got SE squared is equal to SB squared. Oh, you're right. Okay. So, whoops, what did I just do there? So let me hide this, and now that will give me some more room for the proof. I'm going to hide O1, O2. So gamma 1, gamma 2, and the point circle E. E. All right. So any point on this radical axis will have the same power with respect to all three. Respect to all three circles. And so wherever M is, so I'll say any point M prime. And so set M prime to be M in the problem, and then that solves it. So the point M in the problem lies on ST, since it has the same power with respect to lemma 1, and the point circle E. So applying this gives MF equals MG. All right, so now we'll move back to the problem we didn't solve yet. All right, very nice. So we have about 10 minutes left. Let's see if we can get anywhere on this one. These are hard problems, but yeah, we're not doing bad. You see Serdar hopped off. All right. Okay. So we wanted to show that CMB and BHI were similar. And we tried a couple things to move points around. I'm going to delete this circle for a second. So J is the midpoint of FG. Yeah, can we show BM over BH is BC over BI? Yeah, the point I is defined in a really weird way. We have to use that I lies on FG. That's kind of what I struggled with in the beginning. So yeah, we use the reflection property because that means that angle HBI is equal to angle HBM by symmetry. So, but also, if we can show angle BHI is equal to angle CMB, then that would solve the problem. So, but we want to show triangles CBM and BHI are similar. If we can show that, that solves the problem. So yeah, CMB and IBH. I'd like to make it, I'd like H to be the midpoint of something, but I don't see what. Let's see. Yeah, it would be nice if H were the midpoint of something. What if I reflect A across H? Well, actually, let's see. I don't think IHA is similar. Let's see. Angle IAH is 88.5. Is this, I doubt this is 88.5. Oh, it is. I think that is a step forward. Oh no, 88.8. So close. So close. The GeoGebra is never wrong. Oops. Yeah, so we want to show a spiral similarity takes MBC to HBI. Any tricks with spiral similarities that might be useful? What if I label this point right here P? Can I show BIP is similar to something? BIP, FG, really, FGDM? That almost surely would seem like it would help. FGBM and JPBM. Okay. Sorry. So yeah, I never tried showing. Can we show angle B? What is angle BPI? So angle BPI. It's kind of interesting. BPI, that is 62.4 degrees. Can we get a point here somehow that gets 62.4 degrees? Not sure. Is anything else? Because if that's cyclic like you mentioned, then JMB should also be 62.4. And so that would mean that yeah, what if I draw like the parallel? So this is getting a little crazy, but MJ bisects CH. Interesting. MJ bisects CH. I mean, maybe CHFG. So yeah, there's a bunch of things I'm looking at. So it's interesting that JPHB is cyclic. So All right, we're out of time, but I think there's a lot of really interesting ideas here. So if any of you on YouTube end up figuring this out, feel free to post it in the comments of my video or on Discord. So thanks everyone for participating today. We had a good group, and I see someone just hopped in at the very end. So hi, Luat. Thanks for joining, but I'm sorry, we were just about to finish the last problem. So yeah, if you can make it next time, that would be awesome. And if any of you want to join, feel free to email me at mgreen801@gmail.com. And like I mentioned before, it's at 10 a.m. US Central Time. So thanks, everyone. All right.